Thank you all. Hello everyone. I'm Xiaodan Wang from Fudan University in China, and today I would like to share you with our paper, Agree, Aligning Cross-Modal Entities for Image Text Retrieval upon Vision Language Pre-trained Models. The image text retrieval is a challenging cross-modal task, which requires to retrieve semantically correlated text or image samples for a given image or text samples from a predefined database. The key challenge in image text retrieval lies in how to do representation learning for both image and text, and then measure the cross-modal similarities between their representations. Recently, with the development of vision language pre-trained models, it has shown increasing power on greatly improving the performance of many cross-modal tasks, including image text retrieval. Despite their success, however, the current VLP models have not yet realized a fine-grained cross-modal semantic matching mechanism. Although some fine-grained cross-modal association like object token or patch token correspondence are explored, VLP-based image text retrieval methods may still output incorrect retrieval results where the entities cannot be aligned. See the three mismatched cases in Figure 1. In the cases of Wukong fine-tuned on the dataset CocoCN. In the first case, the pineapple in the query does not appear in the predicted images. Similarly, in the second case, the model only pays attention to the matching on vegetables and plates, but ignores another important entity, kimbap, and also it has a misjudgment on the number of plates. In the second case, the predicted task does not contain apple and cake, which can be apparently observed in the query image. Recent efforts try to fix this problem by emphasizing the correspondence of cross-modal entities in the pre-training stage of VLP. Some work constructs thin graphs for the images and text, and then align them, while others leverage external knowledge, such as multilingual datasets, for proving. However, the improvement on the pre-training stage is of highly computational cost, and the full training data is not always publicly available, which further decreases the practical value of these approaches. Besides all the shortcomings, the current methods also do not observe the inconsistency long exists in images and text, as the figure shows. Where the captions are always concise but important, it contains few entities, while the images usually contain abandoned entities, which needs to be filtered for aligning with the text. Therefore, we normally propose a lightweight and practical approach named Agree to align cross-modal entities for image text retrieval upon the VLP models, but only at the fine-tuning and the re-ranking stage. The overview of Agree is depicted in the figure. We first identify the textual entities and the visual entities from the images, and then encode them together with the original images and text by the VLP models. After that, we go to the fine-tuning stage, where three different modules are designed to learn the alignment between cross-modal entities, including the visual entity image alignment, text image entity alignment, and textual entity image alignment. Then we go to the re-ranking stage, which expects to refine the top key ranking results with two designed re-ranking strategies, including text image bidirectional re-ranking, the textual entity guided re-ranking. First, let's go to the fine-tuning framework of our method. The fine-tuning framework of Agree is built upon an image text contrastive learning paradigm, where we optimize both global similarity and entity similarity, which in the contrastive learning strategy, which expects to shorten the distance between the related images and text and push those irrelevant ones in the embedding space. The global similarity is gotten by directly calculating the similarity between the embedding of image and text. And the entity similarity is a cross-modal entity alignment similarity between an image and text pair based on our three normally proposed modules. The first is a visual entity image alignment module, which obtains the visual entity pairs from the multimodal knowledge base and then used to learn the alignment between visual entities and their corresponding images by contrastive learning and image region mask modeling. Here we simply use the detected labels as the mediation and reorganize the visual genome as an object-oriented database as our MMKB used in this method. The two submodules, the visual entity matching is to align visual entity label with entity images from the MMKB, and the mask visual consistency alignment is to mask visual entity regions in the image and draw on the difference between of the similarity scores calculated before and after. We minimize the margin ranking loss for visual object consistency learning. Next is the textual entity image alignment module, where in this module we reconsider the asymmetric of the visual and textual entities and pay extra attention to the entity level information in the text. The TEA module construct multiple sentences using the entities and their visualizable properties detected in the text, and learn the alignment between the sentence and its corresponding image through the contrastive learning and the textual entity mask modeling in the text to align with the corresponding image. The TEA consists of two submodules. The first is the textual entity emphasizing alignment, which we consider the entity tokens as extra positive text samples and to stress them. The mask entity consistency alignment, where we mask the textual entity tokens and recompute the original image and the corrupted text as we do in the visual part. The next is the text image entity alignment, and this module is to further bridge the gap between modalities and compensate for the disordered vocabularies between heterogeneous information. We utilize the pre-trained GLIP method as the anchors to identify the region of each entity from the text in the image. And then we mask the grounded visual regions and still maximize the margin ranking loss dissimilarity. Next, we go to the re-ranking stage. The first is the entity-guided re-ranking. And this method is specially designed for zero-shot scenarios, where we transform the textual entity image alignment module in the fine-tuning stage into an entity alignment score and used to re-rank the top K candidates after global similarity selections. The entity-guided re-ranking score is calculated with the combination of the two submodules in the TEA as we talked before. And the next is the text-image bidirectional re-ranking. This strategy is to compensate for the inconsistency brought by the incomplete information in one modality, and we compensate for the inconsistency by information from the complementary modality by reverse retrieval. Our approach only rely on the cross-modal samples themselves as the reciprocal neighbors. Specifically, we see the text samples with the highest similarity as the reciprocal neighbors of the image, and oppositely retrieve the most similar images for each text and utilize the ranking position only to re-rank. The top K candidates is re-ranked with the newly computed positions. Next, we conduct extensive experiments on both Chinese and English VLP models with datasets in two languages, as the statistics shown on this slide. And the next is the fine-tuning results on Flickr 30 kilogram and COCO-C, and one is for English dataset and the other is for Chinese. We compare our method against many approaches. These approaches may include complex attention interactions using object detectors, as well as some innovative researches. Compared with fine-tuning on large-scale VLP model using only global similarity, our methods show great improvement, significantly higher than the fine-tuning results on the VLP model, and prove the effectiveness of our entity-based strategy. On both Chinese and English datasets, our approach is higher than the knowledge injected pre-training methods. The improvement is mainly reflected on the results of recall at 1, which can be explained that the VLP model's strong fitting ability pre-trained on a large amount of data. Our improvement mainly lies in optimizing the re-ranking results to move the ground truth to the front so as to improve the recall. For the zero-shot re-ranking results, the results show that the mean recall of both image text and text to image can be improved. For the dataset, a Chinese commercial dataset, 木哥, it only contains text to image retrieval results. The reverse retrieval also leads to apparent improvement. Moreover, the boosting of text to image is more obvious compared with that of image to text, which further confirms our suggestion that the inconsistency lies in the richness of image and text information. With a richer and more specific description of the image through the image to text reverse retrieval, our method can better assist the text to find a more suitable image. For our method under few-shot scenarios, we randomly split the training set of COCO-CN into 5% to 50%. And we can see that when the amount is quite small, the results show a significant improvement with agree and can better can achieve or even succeed the results with a larger amount of data using the baseline method. We consider this provide an efficient way of fine-tuning. Focusing on the alignment of entity-level information during fine-tuning can greatly reduce training data dependencies. Also, to demonstrate the importance of visual and textual entities, we present different variants of our proposed methods. For the impacts of entity learning, the retrieval performance on the individual model show that the increase brought by visual and textual entities, indicating that the aligning cross-model entities is crucial. Besides, the great improvement by TIA module shows the visual grounding in TIA makes the correspondence between the cross-model entities more specific. For the combination of different modules, we can see that the introduction of TIA will eliminate the contradictory phenomena of utilizing image and text entities at the same time. When aligning visual and textual entities simultaneously, it is quite necessary to build a bridge between them. That is a TIA module in our method. Next is the several examples presented to intuitively present the importance of aligning cross-model entities. Well, as the figure shows, the top 5 images with agree contain more entities corresponding to the query. For example, the top 1 results using baseline of pineapples, bananas, and oranges in a glass plate does not contain the important entity pineapple, but with agree, we can easily align the important entity. And for the image to text cases, the image query in the first row is more accurately matched to the text with entities in the image, including a place of pizza, bottles and pots, which shows that our method pays more attention to the consistency of multiple entities in both images and text, and thus optimizing the ranking results. And here is the conclusion of our paper. And due to the timing limitation, and thank you for your listening.